Alright, it's time to get started. So this is the state where we was last time. So we have a bug somewhere in our CPU that does not let us run the Snake game. So all we know for the moment is that the portion of the memory that corresponds to the graphics are not being updated. And I have a couple of ideas to how to solve it. One of them is making a memory viewer. The other one is making a tool class for picking into memory changes. So the idea is our memory class can register observers. So let's rename that a tool observer class. To emit signals on specific memory address or range, read write. Operations. So this is a better description of what I wanted. So this is a good way to solve the issue, and I may start for this because it's really easy to do and I have a clear idea of how can I make it. So let's put it in progress, and this is an enhancement. Okay, it failed. Another try, and this is an enhancement, and let's get started. So this will be not a test part, it will be part of the interface. So let's create a new script, and this will be a memory observer. Remove all of this, class name, do I want some kind of prefix for the class name? I suppose it's too late for that, so let's start over with that. So we are going to have a memory observer that extends ref counted. So when we initialize it, we are going to pass a memory. A range from integer, this is of type memory, and a range to and a kind of operation. So I will create an enum for the flags. Let's name it observer flags, and we are going to have read, we are going to have write, and read write that is equals to read or write, and default is gonna be read only or read write. We can also not have a default, I guess. Yeah, let's make it react right. And I am forgetting all the commas. So p flags by default is gonna be default. So having these properties here means we want to store them. So this is gonna be out memory of time memory type memory equals null. Bar range from integer bar range 2 of type integer, and this will be from 0, and let's make this 0xFFFF. This is just descriptive. It will be overridden anyway by the init. So let's start a sequence. Assert memory out memory is not null. Assert p range from is bigger or equal to 0, and p range from is less or equal to memory. Do I have a size? No, I don't have a size. So let's do a size method that proxies. Let's make func size returns an integer, and will return private memory.size. So now we can check the memory or the size of the memory. So it needs to be less, not less or equal. And this assertion will say range from is out of bounds. Range 2 should be more or equal of p range from, and less than memory size. So this means we can check any range. So what is this saying? Oh, default does not exist, and that is because this is observer flags.default. Okay. Now we can start assigning memory equals out memory, range from equals p range from, range 2 equals p range 2. Yeah, and that's mostly it. And we are going to also have a signal memory read, and we are going to pass the address and the value. Both are going to be integers. And another signal memory write address int old value new value. So we can use these signals to pick into the range of memory and the kind of operation that we care of. And the point is when we initialize this, we are going to register our observer into the memory. So we are going to say out memory register memory observer and pass ourselves. So now we can create this function. We can even make it internal and say this is a friend class. So we are explicitly saying that a memory observer will call this function. So even better, we can make the create memory observer part of the memory. And this one will return a memory observer, and we have the from to and flags functions from here. So we are going to say var observer equals memory observer dot new, and we pass self. And we no longer need to call register memory observer. Instead, we are going to create the observer from this function. So this will be self p range from. We have done the assertions already, so we don't have to repeat them. P range to P flags. Yes, this is not observer flags, this is memory observer flags default. Okay, let's add some lines to this for readability. And this function should return a memory observer, so return observer. And we are going to have an internal variable observers of type array of observer. So we also are going to have a func remove observer and pass a memory observer as argument. And this one is going to remove it from the observers array. Eras out observer. So the reason for the out prefix means that this object is going to be modified, and that is kind of the point. So we don't have safety, access safety. Everything is public in GdScript, so we need to somehow find a way to do that kind of job for ourselves. So now we can add our new observer to our observer list. pushback. So we have read and write operations, and hey Cricket, are you feeling lucky tonight? So the good thing of this is we kinda don't care if memory is being read or write 8 or 6 bits, because we can use flags for it, right? So we can use read 8, write 8, read write 8, and another version for the 16. So we can do this, rename this to 16, rename this to 16, and now I'm going to change this to have some indentation, and this is going to be 0x1 shifted by 0, x1 shifted by 1, x1 shifted by 2, x1 shifted by 3. So now we have a bit flag. Default is going to be read write 8. So now we can implement all the stuff. So we can say we can go emit, read, and pass the address and value. Right before returning, and a flag, in this case memory observer flags read 8, because this is an 8-bit read. So now let's rename it to emit observer. So let's create that function, emit observer, and the address is going to be an integer, value is going to be an integer, and observer flag is going to be a flag, of course. And the operation will be a flag, an observer flag. So now we can say that we can iterate observers. For observer in our array of observers, and can I enable over scroll? Auto save interval, content intent, and save scroll. Scroll past end of file. This is what I wanted, so now I can scroll some more. Awesome. So observer is of type memory observer, and I can say if observer dot flags. Oh, I never created the flags variable. My bad. Integer will be equals to observer flags dot default. If observer flags and the operation, this means the observer is listening this kind of operation, and we are going to emit the signal. Observer, and we are going to call the memory. Sorry, what is memory read or memory write? So I will now ask to match the operation, and in the case of memory observer flags, okay, dot readd 8 bits or readd 16 bits. We are going to emit memory read with address and value. It is p value actually, and in the case of write 8 or write 16, we are going to emit memory write. So I forgot to call emit here. So what I am missing? Cannot resolve member init. And why is that? Because it just needed to finish. Okay. So it has finished parsing, and now we have an observer class that we can use to check when something changes. So we can say we can use our knowledge of the memory mapping to find out when stuff is happening. By the way, Cricket or anyone, is the music too high? Can you hear me okay? So we know the memory of the number generator, we know the value of the last pressed button, we know the range of the screen mapping. So exclusion code, execution code, and the game was introduced in this article, and over here, somewhere over here, there is a link to the full game in assembly. Okay, here is the assembly code. Let's open it in a new tab. So here is the snake game, and here is some information of the screen. So we know that in the first 2 bytes there is the location of the apple. So the first byte is the less significant byte, the second byte is the more significant byte. So we can look at that. So let's go to our test snake script and start adding observers to our CPU. So let's say CPU create memory, no, CPU.memory create memory observer, and now we are going to observe from memory 0 to memory 1, and we want only write memory observer flags read write 8 bits. So we want to know when any of those values changes. So bar apple observer is going to be this. Okay, so I think we can even define it here. Let's get some more space, because as soon as the CPU is created, the memories are already created, and we can start creating the observers. My only question is if the memory is populated at the moment of the initialization. So let's take a look on that. NES CPU. Do I have an init in here? Blah blah blah. Yes, memory is initialized with the right size at that very moment, so it is safe to do that. So now we can have an apple observer and a snake head observer, and the snake head is stored in the 0x10 and 0x11. I am assuming, is this hex or not? Because it is not. I assume yes. It is not showing 0x first, but this is not showing either, and it has FF, so I am assuming this is hex. So yes, this is 10 and 11 for the snake head. Next is the snake body observer. And we are going to check from the range 12 onwards. So let's go from 12 to, let's say, 22. I only care when this changes, so I don't care when it is read. So let's say write alone. So I started creating this and I did not finish my changes into the memory for this. So we are checking of the flags, but we are not changing the range of the address. If p address is less than the observer top range from, or p address is bigger than the observer range 2, then we are going to skip it. And then if AND operation equals to 0, then we are going to skip it, and then we can make the match for emitting the signal. Oh boy, I will close Steam because it's annoying. So now we have pretty much what it is. So we don't need to pass the value unless it is the new value. Right, so that is why I was using two functions initially. So yeah, so let's just have two values, odd value and new value. And in the case of reading, we are just passing the same one. Yep. So we choose the same value as the new value for the read. So in the case of memory read, we are going to pass value old, and in the case of write, let's pass value old, p value new. And this is kind of all we care about, and we just need to call the functions in the other cases. So we have memory read in memread, memory write in this case, and now I can remove this print because now I have the observer that I can use. Now I can have a memory read write, the new value is going to be p value when writing. When reading 16, we are emitting read 16 and passing the same. We are passing this as result. Var result equals of type int equals to this, and we pass result as old and new arguments, and write 16 the odd value is kind of tricky. We will need to do the reading if we want to write to make it happen. So instead of calling memread, let's access the memory address directly to avoid the execution of the observer. So let's do this and this, and the odd value will be this, and we can now pass the odd value. So this is going to be odd low and low high. This is odd high and odd low, and this needs to happen before I am reading, right? So the old value is going to be odd value, and the new value is going to be p value, which is the one that we are passing as argument, and this is going to be write 16. So if I am not crazy, we are finished with our observer class. Now we can create any kind of observation. So we can also observe our screen. So we can watch from memory, as this says, 0x200 to 0x600. So 0x200 to 0x600, and this is a write 8 operation, and we can now have a screen observer, and we can forget about all these screen changed stuff. We don't need the screen changed anymore, because now we have the observer, and we are going to get a specific signal for a specific address whenever a bit changes. So this is much more effective than looping the entire memory mapping every single time something changes. So we can do, instead of screen changed connect screen render, we can comment that for now, and we can say screen observer dot memory write connect, and the function is going to be update screen pixel. And now we have to create our function update screen pixel. Actually, for the sake of style guides, instead of connecting this to a function, I will use this syntax, this style. So I will use the prefix on, then the object that is emitting the signal, the screen observer, and then underscore and the signal that is being emitted. And this is the function that I am going to use for the signal connection. So now I use my function on screen observer memory write, and I know from this function that just reading the function signature, I know that it is connected to a signal that is being, to what signal that is being emitted from what object. So this signal takes these arguments. It emits the address, the old value, and the new value. So I will add some prefixes, and we actually don't care at all of what was the old value. So I will put an underscore in front so it does not generate a warning. And for now it is going to be a to-do. My music suddenly stopped. Let's fix that. By the way, yes, this is correct. There we are. And now this function is just going to call update the screen pixel with the address and the new value. And instead instead of the address, it is going to be pixel index and color. So for the pixel index, we can look at here that it uses where is it getting the texture is child I, and I choose the memory minus 200. So it is going to be address subtract 0x200, and that is going to be the index of the pixel, and the new value is going to be just CPU by to color, and pass the new value. And now this is the real to do. So let's see what it does. So now we need the pixel texture that we are just getting it from the pixel index, and we are going to call self-modulate on it using the P color, and that is all. All of this has been replaced by these 3 lines of code using our memory observer. It seems to add a lot of overhead, but right now we only have 4 observers that are executed, and we are not watching to every single operation that is happening all the time. We should care of when a byte is being written on them. So most of the time the observer are going to be skipped. So we don't need the screen changed anymore. We don't need that signal at all anymore. So we can in theory remove this signal. We don't need anymore the last screen buffer, and we don't need anything of this. We don't need prints anymore, and I think all of this has nothing useful at all. So we can get rid of the entire frame start variable, and all we have is last button pressed, and this await is taking care of having some kind of faked threading. So let's try to run it now and see what happens. Okay, so we have an insertion, and size is null because memory is null, and that is because I have not yet assigned memory, so I have to use out memory. Dump error. And now pixel modulate pixel texture self-modulate equals p color, and that is because get child returned null, probably because I did this before ready, but that should not be happening. So let's go one step back, and what is the address that is changing? The address is this value. Let's open our calculator and let's convert that decimal 1536 into hex, and hex is 600. Okay, that is interesting. And the new value is 32. So interestingly, something has been assigned, and we thought it wasn't. So and what has failed? So in this case, pixel index is 1024, and how many pixels do we have? 1024, but it should not be 1024 because it should be 1023, the top one, shouldn't it? Or are we missing 1 pixel? Oh, we are indeed missing 1 pixel. So let's duplicate this, and now we have 1025 is maximum. And run again and see what happens. And indeed we seem to have 2 values in here. I don't remember, maybe we set this manually. I don't know. So for the start, in ready, let's clear the screen. So let's create a function func update screen, and let's do this. So let's take a slice of the memory, screen frame equals to the CPU memory slice, and we are going to take from the 200 to the 600, and this is a packet byte array for E in range screen frame.size, and we are going to iterate over this and say update screen pixel E with the color CPU dot get, no, it's byte color, b new value, no, it's not b new value, sorry, it is screen frame sub I. And what did I do wrong here? Why it says it's a lambda? Oh, because I wrote func instead of var. That was dumb. Okay, so now I can let's call this one refresh screen, and I can call refresh screen right before anything else. And now I should start with an fully empty thing. And now I am wondering, why is this that value? So something funny about the The by to color function only takes in consideration the first 0 to the first 15 colors, but that a byte can take up to 226. So what we are going to match instead of byte is the modulus, the mod of 15. So if it goes over 15, it will start again on 0. So it can be black again. So question, should be modulus of, no, I don't know. I don't know if I want black to be repeated because it's the clear color, and sometimes it could get weird, right? So we can do byte -1. No, we can't. We can do if p byte equals 0, we can return black. And otherwise we should return a different color instead of black. What can we return? Can we use violet? Is it different enough from the other ones? This could be dark magenta, and I think that is enough difference. So now this is gray, and gray is a 2 or a 9, and it is apparently never changing. So question, why is it ever changing? We can put a breakpoint here and rerun. Remove this and put a breakpoint here now, because this was running in the refresh screen loop first. So now we are getting the pixel changed with the color gray, and we are getting a memory write function indeed. So the old value was 0 and the new value is 32, and we have a memory write operation, and the memory write operation is happening by the load function. Oh, so the first function, the PC counter is starting at 600. So the end of the memory was 05FF, not 600, and that was the mistake. So now I am concerned about something, and that is that I am missing a pixel. What is wrong? Maybe nothing? So my observer needs to read up to 05FF. Now I can start over, and if I put a breakpoint, it is never reading, right? So the thing is that I also need to change this. What else did I need to change? So this about to execute the instruction, the screen buffer is unused, so I can remove this completely. and this screen frame is just to 5 ff now. So let's take another look, and I forgot to remove this because it's doing the first clear. Now, is it doing something? Okay, here it is. Now I have a couple of variables, a couple of pixels drawn, but we don't know what they are. What if I put a breakpoint now? Is something changing? Okay. So I can do if CPU is running breakpoint. So let's try that. Okay, now it will only make the breakpoint if the CPU is running. So we can try in example to check to observe the last preset button. So we can Apple observer memory write, connect on Apple observer memory write. Now I create this function. I need the same arguments, and I can print Apple let's use an argument like this is now at location, and another argument post. Was it like this? Now dot format, and make an array with the first is X or Y depending on the address. And the second argument is just the value. And let's just try it for now. And does it print? Yeah, so the Apple location is changing, and I don't know exactly why is it changing over time. But only X is changing, isn't it? Oh, right. So this is the X. It's not X and Y. It's just a pixel index using 16 memory bytes. So this is low and high. So I don't know. Depending on how the code is written, it could be writing 2 bytes at the same time, or could be writing 1. So let's try to write 16. Apple observer write 16 and see if it writes the 16 bytes all together. So first there is no first argument, it is just this one, and location is going to be p-value. So the thing is, I wanted to format this as a hex. And how did I format a hex? I erased the old print that I was using, sadly. But maybe I can resurrect it. I think it was on memory. So let's start undoing. And I have it in here. Copy and redo everything. This is how we do it. So I will put this print in here, and I will use this in here. Apple is now at location this. So it is changing. Now I wonder, why is it emitting the signal twice? We're only reading the right 16. So let's put a breakpoint in here and see both executions. So first it's going to execute the big number, and the observer is coming from right 16 as supposed to, and it is doing a mem write, but this is write 8 bits. It is not write 16 bits. So P operation is true. Oh, I see. So I have done something stupid. So I am emitting the signal for any of the cases. What are observer flags? Observer and flags equals to 3, and the operation is true, so it is write 8. So this is the apple, and the apple was registered as write 16. So the question is, why is the apple observer registered with a 3? Maybe because no, I did set a flag. Create memory observer, create memory observer has a p flags. I am passing p flags, and in the default I am not setting flags, and that was why it was a little weird. So now it is not printing anything, and that is because it is writing 1 byte at a time instead of both at the same time using the assembler instructions. So that is a little sad, but is understandable because it's a pointer, it's not a something. So when writing this value is going to write first the low and then the high. So we can use that So I am wondering why the apple position is changing all the time. It shouldn't be changing all the time. Unless the snake dies or captures the apple. So before becoming crazy, let's make some more testing. So let's change for write 8 before, and let's make the same observation for the head of the snake. And this one, let's make the snake head observer, and let's make on head snake observer memory write func on snake head observer memory write, and more of the same. And this is snake head is now at location p new value, and this is on. I also want to reorder this to put the screen observer after, because I created it at the bottom. So now we can print both the apple and the head of the snake. So interestingly, the apple is moving but the head is not. So it could be that we are wrong of what is each byte. So let's make some stuff. So first part apple and make it an integer equals 0, and let's change this a little. So if p address equals 0, because the apple is 0001 and 0 is the low significant byte. So apple and equal F0 apple or equal new value. So the idea is we are removing the last 8 bytes with this AND operation and then setting the new 8 bytes with this. And now elif address equals 1, we are going to remove the second bytes and we are going to put the second half in the second byte position. And now we can use apple in our print instead. And because it changes first the low and then the high, we can put the print in this second change. And let's see how that looks like now. So Apple is now in 20E, then in 5E, 5, 7. So it is moving very randomly. And we can change that a little more. We can turn that into X and Y position. Oh. Bar pixel index equals to Apple minus 0x200, and now this is an index. Now we can have X and Y columns. The X column is going to be the modulus of the width of the screen, 32, and that X is the column, and Y is going to be equal to the division pixel index divided by 32. This is integer division. It should not make any error, and we can now make add X and Y to our print and know the coordinates of the apple. So now we know that it is 324, 15078. So we have a more clear idea of where is the apple supposed to be located. We yet don't know what the hell is going on. We don't know why is this changing so randomly. But we have a more clear idea of what is happening in the memory. So it is indeed not moving one pixel at a time. So next, so now we can make the same for the head of the snake instead of the apple. Bar snake head integer equals 0, and we can copy the same and put it on the snake code, and we are going to replace apple for snake head. Replace, 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 replace. And we can change this part of the print so it shows the position of the snake head instead of the apple. And we need to change the memory where the snake head is located, which I believe is 2 and 3. Correct? No, actually it's 10 and 11. Sorry about that. So it's 10 and 11. So now we can why is this throwing an error? X is not declared. It is right here. What do you mean? Oh, because the print needs to be moved inside the if. Okay, let's give it a run. And now the snake head is at 116. So the snake head never moves, the apple is changing very randomly. So something is wrong indeed, right? So now we have a more clear idea of what is happening with the members of the snake. So I am under the impression that it is jumping back to the start and starting over. It is initializing over and over again. And that may be for one of the branching or jumping that is happening. So this is jump subroutine. And then return. And this is jump subroutine to init. And then it's jumping to loop. So this is the first things we are going to be looking at. So the first instruction is supposed to be the very first instruction into all disassembler is jump to subroutine. So let's see if that is correct. Jump subroutine is instruction 20. So if we look at our game code, it should start with 20, and indeed it does. And it says jump to instruction 6. Subroutine takes 1 or 2 arguments. Let's see, it takes 3 bytes, so it takes 2 bytes in our instruction. So it has 6 and again 6, and that means it should be moving to the memory location 606. So this, let's comment, is position 0x600, 601, 602, and 3, and 4, 5, and 6. So this is the next instruction. It's a jump subroutine again. So from jump init it goes to jump init snake. So this wants to jump to 600 from what I see here, because this is less significant. Oh, sorry, it's OD, not 06. So this goes 7, 8, 9, not 10, A, B, C, D, E, F. So it is jumping from 600 to 606, and this is jumping to 600 and D, meaning this one, this position. And this jump is A9, and A9 is a load, an LDA, and the value of 2. So this is loading the literal 2 into the A register, and then storing it into the memory location 2. So it goes store it 85 into the memory location 2, and then it's making another LDA. Let's see, yes, of the literal 4, and another store into memory location 3, exactly, and then is storing, so it's loading. Put the hex number 11 into register A. So it is loading 11. And storing it into location 10. And loading 10. And store it into memory location 12. So the first values are very literal. So it is not random at all. The first apple is located. Wait, this is 2 and 3. This is not the apple. Start direction. Yes, this is the directions. And this is the length of the snake. Okay. Yes, this is not the apple, this is the snake. That is correct. And then it's storing the hex 11, that is 17, decimal 17, into the less significant part of the head location, and then it's loading the literal 10 and storing it. Wait a second, why 12? So 12 should be like this, the position of the second half of the body. Yeah, so it is skipping 2 by 2. Hey, 32. So yeah, so it's on the location. So it is hard coding the position of the first 3 bytes of the snake. So question, is Champ doing the right thing? That is what we need to check in our snake. So for that, let's see what is happening. So we have been reading the first writes of the memory. So we can check all of them at the same time. We can observe all the first zero page observer and observe from 0 to FF, and we check whenever a byte is written on it, and we can say in our ready function, where did I put it? Right before the screen observer. Okay. Whenever the 0 page observer changes, we are going to call the 0 page memory write function. Func this, same arguments, and we can just make a print. Oops. And we can just call this dollars this. Change it. So we can put the old value first, the memory, and then the new value. So P old value, I am forgetting the modulo symbol. P old value, P address, P new value, and this is going to be our memory changed print. So now we can disable these prints, or we can keep them for a moment, and we should check what changed in here. So we can check what is going to see. Alright, so we don't want to observe FE and FF because they are the random number generator and the input reading. So what we are going to do is just ignore them in our 0 page. So the last one we are checking is FD instead. And now we are going to have much less prints, and we can check what is changing and see if it matches our expectations. So now we are going to read again. So it is loading 2 and store it into memory location 2, and that is what is happening. The memory location 2 is changing from 0 to 2. Then it's loading 4 and storing it into 3, and that is what happened here. And then it's loading 11 and storing it in 10, and that is what is happening here. And then it's loading at 10 and storing it into 12, and that is what is happening here. Then we'll load an OF and store it into 14, and that is what is happening in here. And when that happens, it says we have our head location written, and that is more or less what was saying before. So the head is put in the first strip with the decimal 17. In the first strip, that is this one, more or less. That is kind of interesting. Anyway, so now put the hex number 10 in register A, store the value in 12. Okay, the most significant bytes of the head and body of the snake are all set to hex 04. So 11, 13, and 15 are set to 4. So that means that the memory 0x4 10 to 0x4 14 has the bodies, the 3 bytes of the body, and then it is making the return of the subroutine. So I think that some subroutine may be broken, but we are going to take a look to that right now. So this is the part where things may start getting crazy, and we are going to find out that very soon. So now it is making a return from snake, and now it is going to jump to generate apple position. Let's see if that is happening. After generate apple position, it will start with LDA-FE. So it is loading a random number. And storing it into 00. So wait a second. So yes, so it has loaded in here TF into 00, and the Apple location has changed it with that change. LDI-FE, load a random number from FE into register A. Okay, it's loading another random number, and we don't have that because we removed those prints, and now it's making an and logical AND with accumulator. Apply logical AND with hex 3 to the value in register A. Hex 3 is binary 1-1, so only the last 2 bytes of the significant bits are kept, resulting on a value between 0 and 3. So yes, it is making a random number between 0 and 3, and I suppose that is for what is the strip. So it is clearing carry and then add with carry. That will adding a 2 to a random number between 0 and 3 will create a random number between 2 and 5. And store that into 01, which is the most significant value. And as I said, it got a value between 2 and 5, which in this case is 4. It is a little strange that this print happened when the address was 0 and not when the address was 1. Why did that happen? Oh wait, this print happens before this print, that is why. I could solve that by inverting the connection of the signal. So it first prints the change, and then the apple and snake head. Okay. So now we are fine, and then it returns. When it returns, it comes to here and returns from init, and then jumps into loop. And when it starts loop, it will first read the keys, then check collision, then update the snake, draw the apple, drag the snake, spin wheels, and then jump back to loop. So that is a lot. So read case is going to load FF, the content of FF. So that is the content of the content of the input. It is going to compare to this scan code, and if it is equal, it will branch. Because the input is 0, it will never branch, and then it will return. So read case does nothing, and then jumps to check collision. check collision will first check apple collision. It will load a 0, compare it to 10. In case of not equal, it will be done. Because they are not equal at the start, it will always be done and will be returning, so no collision. Next is update the snake. Update snake. Wait. Is it? Check collision. I think I forgot something. So check collision. Check collision is here, and it will check apple collision and then snake collision. I only read apple collision. And this is the snake collision. It will load the constant of 2 into x. And then it will load the value of 10 plus x, so that is 12. It will compare it to 10, which is the head of the snake. So if there is no collision between the head and the rest of the body, it will continue with that and the rest part of the body. Continue collision loop. I don't see continue collision loop. Why I don't find continue collision loop? Oh, here it is. So it will skip. If there is no collision, it will skip. So if this means maybe collided, it will load 11, so the second part of the body. And if it equals, it did collide. Otherwise, it continues because it did not collide. So yes, it is comparing both bytes. It is comparing bytes in bytes. In halves. So it is incrementing x twice because the 2 bytes of the body, and then it will compare x to what is stored in O3, and O3 is was it the direction? No, the length. Yes. So if x equals to the size of the snake, then it didn't collide. Otherwise, it will jump to the loop. So it will go back over and over. And in the case of did collide, it will jump to game over. If it didn't collide, it will return from the collide check. So nothing of this ever writes into the memory. So we are kind of fine with all of this up until now. Nothing of this writes on memory. So this is the last instruction that we have seen so far. And the next is throwing the apple. So I am under the impression that branching could be wrong. Branch equals and branch not equal. Because what I want to check is branch equal Did collide, didn't collide. Collision, collision. Collision, collision. Branch non-equal. Illegal move. Illegal move. Illegal move. Illegal move. So what I want to check if branching ever goes back, because maybe my error was assuming that branching could be a negative value. Don't checking up collision. Don't checking continue loop. This go forward. Spin loop. And spin loop goes back. So indeed, apparently it can go back. So maybe I was not that crazy. Load X 0. Spin loop. No up. No up. Text. Subtract 1 from the value stored in register X. So I have an idea of something more fun, or of something more interesting, and that is, instead of putting this away very randomly inside the function that executes by every instruction. Where is it? Okay, I have this awaiting here, so I think I can remove it from here and I can re-implement func init, and I can do the super and then override the no op. Let's see how I did it on the NES CPU. So let's find the init. So I have this opcode. Let's find the no op. And now go to the test snake. No op. And let's call this next frame. So we can use nope for skipping to the next frame. And we can say instruction set to 0x000B equals to this, and we are overriding the no op. And now next frame is going to await the next frame. So wait a second. So yes, this was inside the class in next frame. Get my loop, and this could be either, wait a second, let's find the documentation. Process either physics process. Scene 3 and scene 3 have signals, and here it is physics frame. We can use physics frame. So when we go, are we awaiting on the call? Let's go to the NES CPU, await, and we can await the call, and that should allow us to have like a more interesting flow of the game. Famous last words. The problem is no OP is never running. Yep, so I thought that could happen, and I wanted to experiment with it. So let's just undo all of that. Okay. So the value 15 changed from 4 to 4. Let's wait a little and change again. So let's see what our instructions do. Branch equal and branch not equal. So address is the value, jump reads from the value, and it is making it a negative. And this is an OR and should be an AND, right? That is probably the issue with branch equals. So let's see if that changes something. And now we have our breakpoint in the rendering. So let's continue. And it is updating the pixel. So let's remove our breakpoints. This is interesting. Let's remove this breakpoint as well. And now we have finally got something printed. So we have an apple and we have a snake, finally. This is so exciting. Okay, so now we have an unknown instruction of 3. And why could that be? So what is the program counter? Program counter is this 1722. Let's find our calculator. 1722, so it is 6PA, but we have already increased the program counter after reading 6PA, so it is -1, and it is 6B9. And if we look at the game code, this is 600. This is 0x610, and this is 20, 30, 40, 50. Let's make some speed on this. Paste all of them together. So 50, 60, 70, 80, 90, A0, B, C, D, E, F. Now it goes 700, 710, oops, 720, 730. I think this is correct. So now that we know that we are on 6v9, this is 6 B, and the column 9 is this column. So this is indeed an O3, and I wonder what happened here. What was the actual last instruction that we have done before this? Because it seems to me like we have done something wrong in the previous instruction. Let's see. Does E4 exist? Let's find our CPU. E4 is compare X. It says it takes 2 bytes. Do we have a compare X? I know we have many compare X. This one is particularly 0 page. Immediate takes 2 bytes. 0 page takes 1 byte. Absolute takes 3 bytes, and that makes sense. So E4 was meant to be a compare X probably. We can check that in here. So we have a compare X with the memory address 3. So yes. So this was meant to be, oops, a compare X to the 3, but this has been written as an argument of another instruction. So let's see what E8 is. E8 is an increase X and takes 1 byte. So it has done the 2 increment X 2 times, and it only takes 1 byte. So that seems alright to me. So I don't know why this E4 is not taking this second byte as an argument. So let's find out what did I do wrong. So E4 was compare X. Let's see. E4 is compare X, and it compares register X with 0 page. Compare X takes the register X and addressing mode 0 page. We're getting the address, which is the 3 address. Reading the value, the result is going to be the subtraction of the two values, and if the result is less than 0, it will make it absolute and flip the flag. Yes, this kinda looks correct. But what I am not finding is why is this the previous instruction not increasing the program counter by 1. So what did happen before? Let's run again. So let's try to put a breakpoint on the compare X. Let's put the breakpoint, wait until it breaks. Let's advance. So we have address and value. Address is 1616, is that right? Address in mode is 0. 0 is immediate? That doesn't sound right. Oh, okay, so that is because the opcode is not. So this is a compare, but it is not compare X. So that's fine. So let's find next one. And this is opcode. Wait a second. So CPX is the one that we care is E4, and E4 is 228. Okay, that is the one that we care. So this is 201. This is 201. I can probably make it better. If P register equals register X and P addressing mode equals 0 page, breakpoint. So I am cheating, yes. Okay, so we got the breakpoint at the point where we want to know what is going wrong, because this is the last instruction before everything goes to hell. Program counter value is, let's find out here. Self program counter value is 1121. Sorry, 1721. Decimal 1721 is 6B9, and 6B9. Give me a second. And let's go to the top. No, this is the NES CPU, not the Snake CPU. 6B9 is exactly this. So it executed this one and advanced one more. Okay, that seems to be correct. So it is getting the address, and address should be the 3 address, because yes, it is getting the memory from the 3. It is reading this, so this is a 0 page address of 3, and the value of the memory read 3 is a 4, and the register has a 4 value. So this result is a 0. If the result is less than 0, it is make it negative, but it is not the case. Result is a 0. So carry flag is unset. Wait a second. Be register value. Wait a second. Compare CPX. Okay. So carry flag is set if X is bigger than M. Okay, so X is indeed the value. Okay. Not the result. Okay, that is fine. 0 flag is set if X equals M, so this will be set to true. And negative will be set if value is less, if the register is less than the value. Is that correct? Wait a second. Set if bit 7 of the result is set, but compare X does not modify. Does it? Say set if bit 7 of the result is set, but what is the result? Okay, I guess this would be setting the bit 7, and this is the condition that sets it. So yes, this seems to be correct. So now we have current PC is 1121, program counter value, select program counter value is 1121, so it is equal. So the value takes instruction, and size is 2 minus 1, so it will advance. So opcode will be written, and it is 440, not a 3. So it runs a couple of cycles. The second time it works, it seems to work differently. So we seem to have an error somewhere else that caused a wrong shunt. So we fixed branch equals, but we have a similar error. So compare register works properly, but it has only triggered once, and the second time it did something wrong. Okay, so we have this shunt. Branch if flag matches. So we can absolute takes the absolute value, indirect reads the address value, and then the address from that address, some comparison. So I know this has been explicitly copied from somewhere else. So jump to subroutine could be an issue. So it is pushing to the stack the program counter, and maybe return from subroutine is doing it wrong. So addressing mode is always absolute, so it is program counter plus 2 minus 1, 2 because of the absolute. So we know the jump is happening properly. Let's take a look to the return, maybe. Return from subroutine is just setting the program counter to the pop plus 1. Before it was doing minus 1 and now it's doing plus 1. So that looks kinda correct to me. So let's start over and let's see. So it is jumping. Program counter. So it will be storing 1538, and now it is going to be storing. Let's write it up somewhere. Okay, finally found it. New file. I already forgot previous. It was maybe 1538. And now the program counter now is 1544 because it is plus 1 plus 2 minus 1, which is equivalent to plus 1. And let's continue. And now it's returning, and when returning it should assign 1543. So let's advance one step, and now the program counter should be 1543, not 45. That doesn't look correct. So let's start over. So now the program counter is 1537 and it should be pushing 1538. So let's get into, and the address is 1538 indeed. Let's continue. And now the program counter is 1543, so it should be pushing 5044. Red. And now it is returning from the subroutine, and it is going to pop 16 and the returned value is set to the program counter, and now the program counter is set to 1545, which is 1544 plus 1. Was that the what should be happening? Give me a second. Where is my breakpoint? Yes, it's a plus 1. Yeah, it was 45, not 44. That was dumb. So this was removed from the stack. And now we continue, and it is making another jump, and it is pushing 1546 plus 1, 1547, and it should be returning. And when it returns, let's advance one step, and the program counter is 1548, which is one more than 4. So this part seems to be correct, but at some point it should be breaking because it is pushing some unexpected value. So let's continue until the pop does not return what we expected. So right now program counter is 1549. Now program counter is 1540. Oh, it's making another push. And another push. $15.93. Actually, plus 1 is 94, plus 1 is 41, and I think this is 1550. Now it is returning, and after the return, the program counter is 1595, which is one more than this. and remove it from the stack. So that looks correct. And now it's making another jump. So this is going to take a lot before I can make something useful from it. So I think I will do this. So I will add prints instead. Push it. And that is for the jump. Now pop it and choose a value. And actually the push it also can choose the value. Oh no. We're saying what I push it and what I pop it. So what I pop it is -1. Okay. And what I want to do to make this easier to read is removing this print. So let's see what happens now. Remove this breakpoint. And now it's asserted, but I should get some values. So push it this, push it this, pop it this, push it this, pop it the same, pop it the original one, push it this, push it, pop it, push it, push it, pop it, push it, pop it, pop it. This 1590. So let's copy this because I am going to get crazy otherwise. So let's remove some prints and let's add some indentation. So this is push and this is pop, push, pop, pop, push it, pop it, push it, pop it, push it, pop it, pop it, push it, pop it, push it, pop it, push it, pop it, push it. Okay, so let's see this. So it pushed this, push and pop, pop it the same one, so this close it, push this value, push it and pop it, push it another and pop it that value, push it and pop it, and then this is popping this value. So this is here and this is here. This pop it this value. Okay, we have pairs. Now it is push it and pop it. 45. Push it and pop it. Push it and pop it, and it pushed this value. 1609. And it was not used before. So we get a good idea of what is happening with these prints. So 1609 in decimal is 649, and we can find what was the last subroutine that was running with that, because we can go to, what was it, 649 and find it, 649, and this is where the subroutine starts, and it starts with a 07, which is, oh, I don't like that. Alright, because it loads with a +1, so 4C is the first instruction. What is NES CPU? It's a jump. So the first things that this does is jump. And it is jumping to 638. So 638 is this position. But I don't see that push in here. So something is weird. $17.09. What did I change? $17.09. $49. So this was a jump to a negative value. So it is a jump about the start. That jumps back. Init loop, init snake, generate. Jump, 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 jump. This is jumping forward. Generate upper position, and generate upper position is here. So can this be the jump that is jumping back? So this is jumping forward, this is jumping forward, this is jumping forward, forward. So maybe I can improve my prints. So Yeah, let's use the hex. Wow. I don't like a lot filling the entire stuff with prints, but it's better than anything, right? So here is program counter value, and the second one is return to. So this is the print for return, and let's find the other print. And this is jumped from 2, and we jumped from program counter plus 2 minus 1 to address. So let's do it like this, so we can now have a couple more descriptive. So I can copy it from here, I can play my music, and I can replace this with a little better. This is cropped. Why is this cropped? So copy. Okay. Wait. Why I have to push it? Oh. Let's remove this and relaunch. Okay. Copy. Remove this. So jump it. First, let's remove this, but we can keep it as comments. Okay, so now we can take a little better idea. We make a jump, so this is init. Let's put this on one side and our assembly code in the other side. So first, this is jumping to init, and this is jumping to init snake. And it is setting the snake head, and it is returning from init snake, and then it is jumping to generate a pull position, and it is setting the pull position and returning from generate a pull position, and then it's returning from init. and then it should jump into loop. So this one should be loop. And if we look at loop, this one should be read case. And it's returning from read case. Next is check collision. And checking collision will do a couple of stuff. We can check it. Check collision is going to check Apple collision. And return from it. And check snake collision. And return from it. And then it's going to return from check collision. So up until now this seems to be correct. So it did read case, check collision, and now goes to update snake. So this jump is to update the snake. And this seems to be the return of update the snake. Now jumps to draw apple, which we have seen drawn in the screen. Draw apple and returns from draw apple. Now it's jumping to draw snake. And returning from draw snake. Now it's jumping to spin wheels. And this is where things are getting lost, in spin wheels. So jumps on routine seems to work. So let's check what is spin wheels. It loads a 0, makes an spin loop. It has a couple of no-op. It is decrementing X. Wait a second. Wait a second. Slow the game down by wasting cycle. So this spin loop. So there is some branching happening here. So this is basically burning cycles. So it will be doing this 255 times. Decrease X. It is loading a 0, so it will wrap into 2005. Maybe the trouble is on X. PNE. Branch not equals branch if flag is false. So the jump can be negative, and this is the thing. Is this what I believe it is? Spin loop is this. So we know spin wheels is 772D. So we can read spin wheels in machine code here. 72D. Which column is D? Is this column? So yes. So we have load a 0 on X, which is what is happening here. It's loading 0 on X. No operation, no operation. Decrease X. And then branch no equals. And this should be the offset. FB into binary, and if I set this flag to be okay, can I change it like this? Oh fuck, no, I did not want that because this is 74 bits. So let's go, let's try again. FB. So the binary we want is 0, wait. The one that is a 0 is the third bit. So we want 0, 1, 1, 1, 1, 0, 1, 1. Yes, this would be the positive version, and it is 123. So this is minus 123. That is too much. So what does branch not equal to? Can I try this and see what happens? What is jump? 120. Continue. 123. Yes, that was my expectation, minus 123. So maybe the negatives are not as I expect. So let's see what branch not equals is supposed to do, or branch equals. Let's check once more. 0 flag is set, then add the relative displacement to the program counter to cause a branch to a new location. And branch not equal. If negative, no. Branch if 0 flag is clear, then add the relative displacement to the program counter to cause a branch to a new location. So this seems to be correct. Oh, I am tired. I have to say it. So if the 7th flag is set, we are removing the 7th bit and making it negative and adding 1 after. Is that correct though? Why is it adding 1? So let's take a look to what the tutorial does for branching. So in the previous chapter there is an example of this emulator written in Rust, and here is the CPU. So branch not equals will branch if the status does not have new. So we have a branch function. So we have a condition. If condition, jump is going to read the program counter. It's going to read 8 bits from program counter, and it's a signet integer of 8 bits. So it's doing the job that I am doing. So address equals self, program counter adds 1 wrapped. So it adds 1 and then adds jump as un signet 16. So first it treats this as negative, but then adds it as a positive. I kind of don't like that. What does this mean? I don't know how to read it. Wrapping add. How is if you convert a negative 8 bits into an unsignet 16 bits, what happens in Rust? Let's ask ChatGPT. So it's chat.openai.com. Let's make a new chat in Rust programming language. Given negative I8 variable. How is it interpreted as an U16 value? Let's check if it understands the question. In this example, we have variable negative E8 of type E8 with value -42. To convert it to an equivalent U16 value, we use the wrapping add method to add 255 to E8 value, since 256 outside of the wrapping behavior ensures that the result is a valid U8 value. Then we use as keyword to cast the result to U16. And is that what is happening in here? No, it's not. It's doing a wrapping add directly in the U16. Hmm. So let's edit it. Equals to 0. Converted. Oh, it's U16, no 18. Converted U16. Grabbing at. This is what the code is doing. The code seems to be a typo instead of. What did I write wrong? Oh, wrapping is 2 piece. Okay. This corrected the initial value of converted is 0. Then we use wrapping add method to add the value of negative E8 after casting it to U16 to convert it. The result is stored back into blah blah blah. The result would be, in this case, the wrapping add method performs addition and wraps around the minimum value the type, then overflow occurs. Since negative E8 is -42, we are adding it to converted. initially 0, resulting in a value outside of the range, causing an overflow and wrapping around the minimum value plus the remaining amount. What? I did not understand. So basically, it is just making a subtraction in that case. Well, it's strange that it allows it to do it like this, but not making a direct uh, um, assign. So in this case, it doesn't feel like we are doing anything crazy. Are we ever getting a break? Mm-hmm. Why is it different the first and the second time? So let's see, first time. Can I hold this? Program counter is 1741. Six CD. 6C. This is D. 6C dit. It is F9. And second time it jumps back. Program counter is plop 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 plop. 1843. Seven, three, three. Wait a second. This one. 7, 3, 3. This one, and it's going back FB. So this one. 1, 2, 3. So my question is, why is it returning so much? It is returning by 122. That doesn't sound about right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So each one of these is 16. $122 divided by 16, it's like 7.5. 1, 2, 3, 4, 5, 6, 7.5. Like about here. Yes, it's exactly where we are ending. So why is it jumping that far away? It is jumping with a D0. Right, that is right. 208. Programmer 208. It's a D0. Yes, D0. D0 is supposed to be this branch no equal. Branch no equal, and it's indeed D0, and it takes 2 bytes, and that's all. So why is it FB? Why is it that big? So, and after that, this is a 60. Oh, wait a second. No, that doesn't make any sense. Oh. RTS is 60. NES CPU. RTS is 60. Okay. So why is this so big? So we have 1, 2, 3, 4. This should be 4 behind. So it is a -4. Decimal -4. Change it. And this is oh my god. FB. Okay, so I think I see what is the issue. Um, so I am doing the conversion of negative numbers wrong. ADC is implemented as the subtraction, and B equals not B plus 1. So we have a not. No. Gonna make minus jump plus 1, and does this, is this enough? Okay, at least it keeps running, but it's not doing anything correctly. So no, this is not what was supposed to be happening. And if I put a plus 1 here, okay, it just failed before. So no, that was also not right. Maybe OXFF minus this plus 1. This is crazy. Okay, it just failed before. I am completely doing something wrong. Anyway, this is time for ending. It's been so long, and we are very close. We are more close than before. We have one mistake somewhere that does not let us get the loop running, but we are close to get this started properly. So the spin wheels needs to be updated. We need that loop to be fixed. We need to figure out what is wrong with the negative number. So yeah, so let's find out later, I guess. And see you next time. See you on Saturday. Have a nice one.